everyone, and welcome to our first lecture. My name is Sophie Kreuzkamp. I'm a new lecturer in economics. I joined the department this year, and I'm very happy that this is also the first course I will teach. My research interests are in microeconomic theory, therefore I'm also very excited to talk more about microeconomics in this course. Okay, but first of all, attendance. So I put on the QR code here. Please take a photo of it or copy the code so that you are signed into the class. All right. If someone is late, I will also put this to the side so you can also take a photo after the class. All right. So today I want to talk first of all about the organization of the course, and after that the first lecture, which will be about asymmetric information, kind of an introduction to what we will do over the coming weeks. Okay. So first of all, can everyone see this, especially the people in the last row? Are you able to read this? Okay, great. So, yes, here you see my name again. I also put my email address. In case you have any questions, you can write me. My office is in the Arthur Lewis building, and I will also offer office hours over the course starting from next week. I will announce when and where the office hours will take place in the coming days. Okay. So here you can see the timetable. In total, we will have 9 lectures. Starting today, we will have 5 lectures in a row. After that, we will have the reading week, and then we will have the midterm. The midterm, as you can see down here, this will count 30% towards your over a grade. The remaining 70% will be the final exam, which will take place in January. The format and the structure of the exam has not been decided yet, but as soon as I have more information about this, I will announce this in the lecture and also on Blackboard. So at this point, also everyone should have access to Blackboard. If this is not the case, please let me know. So on Blackboard, you will find this sheet. You will also find all the lecture slides and notes that I will discuss in class. Okay. We will also have tutorials. There will be 5 tutorials, and they will start in week 4. Again, the tutorials, the assignment has not been finalized yet, so in case you cannot make it, there might still be some shifts. So if this doesn't resolve within the next week, please let me know. Okay, so let me briefly talk about the content of this course. So today we will talk in general about information, in particular about asymmetric information. We will discuss some mathematical tools that will help us analyze information in economic situations. This will be helpful for several models we will discuss later, such as choice under risk, if people have not perfect information, adverse selection or screening, when people have private information or take private actions. After that, we will discuss the value of information. Information has a different value for different decision makers, so this is also important whenever agents trade information. After the break, we will talk about moral hazard, Then we will also discuss some applications, such as auctions or bargaining. And finally, we will also talk a little bit about experiments. Okay? The next point, I created a Piazza forum. You will find the link also on Blackboard. Please sign up for this. So the idea of this forum is that whenever you have a content-related question, please ask this via this forum instead of writing an email. The benefit is that all students can participate. So for example, you can also answer the question that another student has. So there's more interaction. And also every student benefits from your question, because I'm sure whenever you have a question, probably 10 or more other students have the same question. Okay. Then I also have a reading list of 4 books that you can have a look at. Let me say that the lecture notes are self-contained, but if you are more interested, want to see more additional material, please have a look at these books. All right. Before I start with the first lecture, let me ask if anyone has a question. Yes, please.
So just on my timetable, next week it says I have tutorials for this class, so I was just wondering.
This is, I understand in the timetable it is still scheduled for week 3, but what is written here is the official announcement. So tutorials will start only in week 4. This is because we need at least 2 lectures to have sufficient material that we can discuss in the tutorials later on. All right. Again, the format of the exam has not been decided yet. This will happen within the next week, and once there is an official announcement to make, I will do so in the lecture. Okay? Okay. So today we will start with the first lecture, which is about asymmetric information. Okay? So we can think of information as just some good, like a good that can be produced, that can be sold, that can be acquired. But at the same time, it is a quite unusual good, and therefore of special interest to us. So for example, information can be privately known by several agents. Agents can have different information. If an agent has some information, they can decide to sell it, but they can also decide to keep it private or pass it on to one or even many agents at the same time. So in that sense, information is a cheap good, meaning that once we have the information, it is very cheap or free to reproduce this information. So for example, if I have some information, then I could just make an announcement, I could write it on the Blackboard, and then all of you would have this information immediately. However, information can also be costly to acquire. So typically, the cost of information is about initial acquisition rather than reproduction. Also, information cannot be actively unlearned. So once we have learned some information, of course, people forget something because there is a limit of attention. but typically it is hard to actively decide to unlearn a specific piece of information. Sometimes we don't know which information people have, but we can still make inferences because we can observe their behavior and then infer what is the information that they probably had before they took the decision. Because information is what shapes an individual's decision making. Also, as I mentioned earlier, information can be valued differently by people with different information and also by people that have different decisions to take. And finally, there are different versions of information. So we have the so-called fundamental information, which is information about some fact. But we can also consider more abstract information called meta-information, which would be information we have about other people's information, which we will later on call as their beliefs about the information of the other agents. Okay, so whenever we talk about information, people mean different things. So in particular, when we ask a microeconomist, and at this point we are all microeconomists, what do we typically mean by information? Well, whenever we want to model information, we think of it as a reduction in uncertainty regarding the decision process that the agent has to take. Okay, so one example would be an employer who decides whether or not to employ a candidate. This employer could acquire information by conducting an interview, reading a CV, reading recommendation letters, and by this, taking this information into account when deciding whether to employ the candidate or not, the employer reduces his uncertainty about the skills of the candidate. Okay, so let us now become a bit more formal. Let us introduce our first model. Okay, so this we call the model of uncertainty. It begins with so-called states or states of the world. And what do I mean by that? Well, the world is basically the object that the decision maker is concerned about. So whatever is important for the decision making of this agent, we call as the world. This might be, for example, different outcomes of an experiment based on which we might take different decisions. And a state, which we also denote by S, is a complete description of the world after all uncertainty has been resolved. Okay, so we use the following notation. We call the set of all possible states in our world capital S. So this is some set of states S1, S2, S3, and so on. Typically, you can think of this as a finite set of different states, but this could also be a continuum. Okay? And in general, uncertainty here means that we do not know the state ex ante. We do not know the exact realization in our world. Okay, typically only one state can be true. Okay, so initially there is uncertainty, we do not know the state, we only know that the state must be in the state space because it must be some description of our world. But at the same time, only one of those states can be true. For example, S1, if S1 is the realization, well then S2, S3, and so on cannot be true. And just to introduce some notation, typically we would say that the state has true. You can also say that state S happens, or that state S obtains. Okay, but once the uncertainty is resolved, we will know the true state. Okay. Let me start with one example. So let's consider the example of rolling a dice. Okay? Yes. Excuse me?
Can you zoom in a little bit? It's hard to see.
Okay, I will. Is it too small? I will try to write a bit larger, okay? So here it's written example rolling a dice. Okay. First of all, let us define the state space. If we roll a dice, we have different outcomes. Maybe you can help me with that. Which are the different states in the setting? Yes, please.
Like begin with 1, 2, 3, 4, 5.
Exactly, very good. So the state space, capital S, is, we can denote this as the set of all numbers from 1 to 6. Is that better readable?
That's better, thank you.
Okay. Typically, also in order to illustrate this, it is useful to draw the states in a so-called state space diagram. You will see that this is important because later on we will introduce some information in these settings. Okay? But first of all, let me show you what a state space diagram is. Okay? State space diagram. This is basically an illustration of all possible states. So here we have 6 in total. 1, 2, 3, 4, 5, 6. And all these 6 states form our state space S. Okay? Let me put this to the side. So now I want to introduce the next piece of notation, which are so-called events. formally, an event is a subset of states. And we typically denote this by A. So here we have A, the event, as a subset of the state space. And we call the set of all possible events omega, so the set of all A, B, which are subsets of the state space. Okay. Let me leave that here for a minute so that you can copy. Okay. Let me make one comment on the set of events. So typically the set of events is closed under the usual set operations, which means taking unions or taking complements. Okay, let me write this down. So the set of events omega is closed under the usual set operations of taking unions and complements. Let me explain what I mean by that. So closed means that whenever we take such a set operation, the product of this will also be part of the original set, that is, of the set of events. Okay? So suppose, for example, closedness for unions means if we have some event A and we have another event B, then by closedness, the event A or B is also possible. Okay? In terms of our set, our state space, this means, well, if we have event A, we know that the state lies in the set A. If we also know that event B is true, we know that our set, our state is in the set B. So if we have both pieces of information, we know that our state is in the set A and B. So this is a possible event, hence it is part of omega. Similarly, closedness for complements means that if we have some event A in our set of events omega, then also its complement, which we denote by the negative of A. Okay, so this is the complement of A. This also is a possible event. Okay. In a minute, we will discuss events more closely in our example, but before that, let me summarize again what is the difference between the state space and the set of events. So the set of states is a set of different elements, the different states. This could be numbers, for example. And the set of events is a set of sets, okay? A, B, and so on, these are already subsets of the state space. All right. So let me put this up.
Sorry, so what was the difference between state space and the set of events?
So the state space is the set of possible states. In our example, this was the set of all numbers between 1 and 6. But the set of events is a set of subsets. That could be, for example, the set of 1, the set of 2, but also the set of 1 and 2. Okay? Let me show this with our example. I think that will make it clear. So, what are the possible events that we could have? For example, let us define the following event. A, which means the number of the dice is odd. Okay? Can someone tell me what is this event? What is the set of states?
1, 3, and 5.
Yes, exactly. Very good. Similarly, we could define B as the number is even. Okay, this would be the set 2, 4, and 6. Okay, but we can have many more events. For example, we could have the event the number is 1, or the number is 2, 3, 4, 5, or 6. These are all events. Okay, note that the difference between this piece and this piece is, this is a state, this is the state 1, while this is the event that the state is 1. An event is always a set. Therefore, we have the brackets here. Okay, so this is a state, and this is an event. Okay? We can have more events. We can, for example, have events that the state is between one of two numbers. We could, for example, have the event the number is either 1 or 2. We could have it is 1, 2, or 3. We could have it as 1, 2, 4, or 5. Okay, so basically any collection of states, any collection of numbers between 1 and 6 is a possible event. Okay, so if you take all these sets, all these events together in a set, then you get the set of events. Okay, so the set of events would be A.
Can you go, like,
Oh, I'm sorry. Thank you very much. Okay, the set of events would be A, B, then all those events here. Okay, so the set of events is the set of all subsets of the state space. Okay, so typically this set of events is a pretty big set. Okay. Any questions so far? Okay, so the next step is to introduce a more formal notation for information, which we call information structures. Okay. So an information structure is mathematically the same as a partition, and I put the definition of a partition here. Okay, so intuitively, a partition is a device that cuts a certain set, for example, the state space, into several pieces. Okay, let me write this down. The intuition, partition cuts a set such as the state space into separate disjoint pieces. Okay, so let us slowly go through the formal definition. So a partition is always associated to a certain set. Here in this course we will always talk about partition of state spaces. So we have the partition of S. This will be a collection of events, A1 to AK, such that the following three conditions hold true. First of all, each event is non-empty, so there are no abundant events in our collection. The second, more important point is that the different events are disjoint. So disjoint means that whenever we take the intersection of two events, AI and AJ, then the intersection is not the empty set. This is the definition of disjoint. Okay? And finally, the set of the union of all those events forms the complete original set, namely the state space. Okay, so what does that mean? First of all, if we look at the third point, a partition is a valid measurement of our world because no state gets lost. We have, for each state, we have an event that is in the corresponding partition. Okay, so we don't leave any states out. And similarly, each state only belongs to one event because of the second point, because the events are disjoint. Okay, so this is a helpful description of information because there's a one-to-one mapping between every state and a certain event. And we do not leave out any states. Okay, let me also give you one example in our in the example of rolling dice. Maybe let me just say that, okay, so mathematically we have described a partition But in our course, whenever we talk about information, we will use the term information structure. Okay, so an information structure is a partition of a state space, and also we will call the different events of this collection, the different A1 to AK, we will call them information sets. We call them information sets because we think of this as follows. We have a decision maker who has a certain information structure, so the decision maker knows whether the state is in a certain whether a certain event takes place, that is whether the state is in a certain AI, and this is the decision maker's information set. The decision maker only knows whether the state is in AI or not. Okay? So let us write down some examples of information structures. Okay? One information structure could be that the decision maker either knows whether the number is high or low. And how could we describe such an information structure? So by high, I mean that the number is at least 4. Low would be that the number is at most 3. So our information structure, our partition, is a collection of 2 events, A1 and A2, where A1 is that the number is low, 1, 2, or 3, and A2 is the event that the number is high. Okay? And indeed, it is easy to see that this is an information structure. Well, first of all, we have 2 elements in the collection. Okay? So if we have a look again at the definition of a partition, then both A1 and A2 are non-empty. A1 includes the states 1, 2, and 3. A2 includes the states 4, 5, and 6. Also, the intersection of the 2 events is empty. A1 only includes 1, 2, and 3. A2 only 4, 5, and 6. And the union of the 2 is, well, the number of all numbers between 1 and 6. So this is our state space. Hence also the third point is satisfied. Okay, so this is in general, if you would have a question like, show that a certain set is indeed an information structure, you would have to go back to this definition and check that all 3 points are satisfied for all events in the collection. Okay. We can also illustrate the information structures in our state space diagram. Okay, so this was our state space, and here we have the information structure high or low. So the decision maker knows either that the number is high or the number is low. So for example, suppose that the true number was 2, but the decision maker doesn't know that. Then the decision maker knows, okay, the number is low. So the decision maker only knows Um, So the decision maker knows whether the number is low, whether the state is in this set, which is A1, or whether the number is high, that is, it is in this set. Okay, so typically we denote information structures with dotted or dashed lines. Okay. Let me put it like that, because I would also give you a few more examples to practice a little bit the information structures. Okay? So the next information structure would be odd or even. We already discussed this. Two events, now we call them B1 and B2, which is 1, 3, 5, or 2, 4, or 6. Okay? And as an exercise, I would recommend that you try to draw this information structure in the state space diagram. Okay, I will give you a few seconds for that. Okay. Can anyone help me how to draw this information structure? Which states do I have to draw together? Exactly. Very good. Okay. So let me draw this in green here. This is the event V1, and this is the event V2. Okay. Now let us also discuss the extreme cases. Both A and B were cases of partial information. The decision maker always knew that the state must be 1 out of 3. Okay? But the extreme cases would be perfect and no information, which are always, in any setting, possible information structures. So let us think of what would be perfect information here. Perfect information would mean that the decision maker exactly knows the number. Okay? So think about what would be the information structure in this case. Write down the collection of events and also draw it again in the state space diagram. Okay. Can anyone tell me what is the information structure? What is the collection of events? Perfect. So if we draw this, we just put a circle around every state in our state space. Okay, so this means we have 6 different events. Let's call them C1 to C6. And the events are, well, the numbers 1, the numbers 2, up to 6. Okay, and please note to always put those brackets that it's clear that you're talking about an event and not about a state. Okay? And finally, the other extreme would be no information. So I will also give you a minute here, write down the information structure and illustrate it in the state space diagram. Okay, so any ideas? What is the information structure we have here? Exactly, perfect. So whenever we have no information, the information structure just has one element, let's call it D1, which is only the set S. Okay, and if we draw this, well, that would be a big circle around all states. All right. So to summarize, let me give you the economic interpretation of our information structures. Can I remove this? Okay. So how does it help us to associate an information structure with our decision maker? Well, we can say the following. If a certain state S is 2, but the decision maker might not know the state because he has only access to his information structure, which might be some collection A1 to AK, then a decision maker which we might also call DM, with an information structure A1 to AK this decision maker can only identify the event AI in this collection such that the state lies in this event. That is, that contains S. Okay. Now we have a formal setup for how we can describe information, but we are interested what we can use this for. Okay, so we want to understand what is better and what is worse information, and we want to have also a mathematical concept for that. Okay, so the next step is to compare different information structures so that we can make statements such as decision maker A is better informed than decision maker B. Or sometimes we will see that such a statement is not possible because the information will be fundamentally different between decision makers. Okay. So we can use this framework to define a version of better information. And intuitively, we say that a decision maker A is better informed than a decision maker B if A can tell us everything that B knows. Okay, let me write this down. A person A has better information than person B if A can tell us at least everything that also B knows. Okay. In order to derive this, the following piece of notation is useful. So for every state S, let us call AS the information set that contains S. Okay, so as an example, what does that mean? Well, suppose we have some information structure A1 to AK, and suppose that a certain state S lies in the set AI, belongs to the event AI. Well, then we know that AS is equal to AI. AI is the information set that contains S. So in particular, that means that different states can have the same AS. In the sense of, suppose we have another state S prime, and S prime also lies in AI, well then A of S prime is also equal to AI, that is equal to AS. Okay, note that this notation, the AS, is not a partition of the state space, because we have, first of all, several events occur multiple times, so whenever at least two states are in the same event, we have the same AS. So this notation, this is useful to compare information structures, but not to define a partition. Okay. So with that, we can now define what we mean by a finer information structure. Okay? An information structure A1 to AK is finer than another information structure B1 to BK prime, if and only if the following condition holds true, namely the information set AS is always a subset of the information set BS for every state. Okay? Intuitively, this means, okay, we can compare two information structures if one can be built from the other one by combining certain events. Okay? So let me also give you an example for this. Suppose we have let us compare the extreme cases, no information, and perfect information. Well, clearly, perfect information is a finer information structure than no information, because here we have, these are the different AS, easier, and all of them lie in the state space. Okay, so here, okay, I know this sounds trivial, but I would recommend you that you try to formally show this using the definition of finer information structure. Okay, so I write this down here. This is like a small homework. Prove this using the definition. Oh, excuse me. Thank you so much for that. Okay. And with this definition of a finer information structure, this is still a positive statement. We can now describe what we mean by better information. Okay? So suppose we want to compare the information of two individuals, A and B. Let A have information structure A1 to AK, and let B have information structure B1 to BK prime. Then we say that person A has better information than person B if the information structure of A is finer than the information structure of B. Okay, so this statement, or this is a good comparison whenever we have a pairwise comparison between two agents. Okay, so whenever we have two people, then we say that we have asymmetric information between those two people if one person, say person A, has better information than person B, or vice versa, if person B has better information than person A, or we say that they have heterogeneous information if their information is different, that is, they don't have the same information structure, but we can also not compare them. Okay, note that there are always three cases. Either the two people have the same information, or they have different information and one has better information, or they have different information and we cannot compare this. So this means the three options are same information, asymmetric information, one is better, and heterogeneous information. They are incomparable. Okay. Let us also discuss the concept of asymmetric and heterogeneous information in our example. Okay. So and let us consider first the following example. We have two persons. Person A has the following information structure. There are 4 different events. The first 3 events are that the number is 1, 2, or 3. And the last one, it is 5, 4, 5, or 6. And person B has 3 different events. Person B knows if the number is 1, if the number is 2 or 3, or if the number is 4, 5, or 6. Okay, so I guess we can easily rule out the case where they have the same information, because apparently it is not the case. Person A has more events in their information structure than person B. Okay, so what do you think in this case? Is it asymmetric or heterogeneous information? Perfect. Why? Can you describe where exactly it's final, or?
I think he has like 1, 2, and 3, and B has none.
Very good, very good. Okay, so the difference is, well, both know whether it's 1 and both know whether it's 4, 5, or 6. But person A can distinguish between 2 and 3, in addition what person B cannot do. Okay, so in that sense, person A can tell us everything that B knows, and in addition, person A can tell us whether it's 2 or 3. Okay, so this is an example of asymmetric information. Okay, and again, as an exercise, I would recommend that you draw the information structures in the state space diagram. And formally prove that we have asymmetric information. Okay, and by formally proving, I mean that you look again at this definition, write down the different AS, and prove that the AS are a subset of the BS. Okay, let me also give you another example. So suppose now person A has the following three events, A1 to A3. Either person A knows whether it's 1 or 2, or 3, or 4, 5, or 6. And suppose that person B has the same information structure as in A. Okay? So in that case, we have asymmetric, heterogeneous, or same information. Does anyone want to try? Yes, perfect. Okay, why is it heterogeneous? Where we can rule out the other cases. Obviously, it's not the same information because the events are different. And it's also not asymmetric information because sometimes A is better informed. For example, A knows whether the state is 3 or not, while in other cases, B is better informed, B knows whether the state is 1 or not. Okay, so this is an example of heterogeneous information. And again, I would recommend that you draw this in a state space diagram and show that this is heterogeneous information. To show that, you again use the definition of finer information structures and show that this is not satisfied in case B. Okay, so more precisely, you show that sometimes the AS are a subset of the BS, but in other cases, the BS are a subset of the AS. Okay. So finally, I would like to talk about probability measures, because we need probabilities to assess how likely a certain event is. Okay. So what is a probability measure? So I'm sure you all have heard about probabilities, maybe even have taken some courses on that. Usually a probability is some number between 0 and 1. And a probability measure is basically a function that assigns a certain probability to every possible event. Okay? So the probability measure is a function p, which assigns to every event in the set omega, so for example to the event A, a certain probability p of A, which is some number in the interval from 0 to 1. Okay? And a probability measure has to satisfy 3 conditions. Well, first of all, that probabilities are always positive. And also, you could write down they are always smaller than 1. I put this in brackets because this point is actually implied by the second one, namely that the probability of S of the complete state space is equal to 1. Because the probability of the state space is the sum of the probabilities of all unit events that each single state takes place. So every event must be smaller. The probability of every event must be smaller than 1 because every event is a subset of the state space. The third condition is the most interesting one, namely if two events A and B are disjoint, then the probability of their union, the probability that the state is either in A or in B, is equal to the sum of the individual probabilities. Okay? Here's the definition of disjointness. Events A and B are disjoint if their intersection is empty, if no state belongs to both A and B. And instead of disjoint, we sometimes also say mutually exclusive. Okay, so now we have defined probabilities, but we are in particular interested in so-called conditional probabilities. Okay, so suppose, for example, our decision maker knows that the state lies in a certain event. He knows the event A happened. Then the question is, how can we describe the probability that a certain event B happens conditional on the decision maker knowing that event A has already happened? Okay? What is a conditional probability? So the probability of an event A, conditional, or we sometimes also say given event B, is defined as follows. Okay? We write it as the probability of A given B is equal to the probability of A and B over the probability of B. Note that conditional probabilities are only well defined if the probability of B is positive. Mathematically, this makes sense because we cannot divide by 0, but also intuitively, we cannot interpret a conditional probability if the conditioning event B doesn't tell us anything. If the probability of B is 0, this this means that B never happens, so we don't learn anything if we know event B, because this can never happen. Okay, so whenever the probability of PB is equal to 0, this is not defined. This is important to the degree that you have to make sure whenever you define a conditional probability that indeed the probability of B is positive. Because otherwise you run into calculation errors. Okay. Let me also give you two more formulas. The first one is the so-called general multiplication rule and also Bayes' rule, which will help us to compute conditional probabilities. Okay? Let us start with the general multiplication rule. Okay? This formula tells us that the probability of A and B is equal to the probability of A multiplied by the probability of B, conditional on A, or equivalently, the probability of B multiplied by the probability of A, conditional on B. Okay? We also call this G and R. Let me show you the derivation of this. This is a very useful formula that will help us also to derive Bayes' rule, which will help us to compute conditional probabilities. Okay, so it is helpful if you keep this formula in mind because we will use it over and over again in the next week. So, why is this true? Well, first of all, note that the event A and B, this means the state lies both in A and in B, or we could say the state lies in B and in A. It doesn't matter how, in which order we say it, this is always the same set. Okay? So this implies in particular that also the probability is the same, because we are talking about the same set. The probability of A and B is equal to the probability of B and A. Okay? And now note that this holds true whenever we have that probability of A and the probability of B are positive. Notice that the general multiplication rule also holds true if the probabilities are 0. In that case, if, for example, PA is 0, then also the probability of A and B is 0. So this one would be 0, this one would be 0, hence the rule still applies. But this case is not so interesting, so let us focus on the case where the probabilities are positive. In that case, we call by the definition of a conditional probability that P of A given B is equal to P of A and B divided by P of B. Similarly, if we switch the role of B and A, the probability of B conditional on A is equal to the probability of B and A divided by the probability of A. And note that we can rewrite those equations. If we multiply by PB, we get P of A given B times P of B equal to P of A and B. This proves the second part of the formula, that this one is equal to this one. And the second equation is equivalent to, if we multiply by P and A, we get P of B conditional on A times P of A equal to P of B and A, or by this equation, P of A and B. Okay, and this one here, this proves the second part, that this one is equal to this. Okay. Let me also briefly talk about the interpretation. So, what is P of A and B? Well, according to the first part of the formula, it is P of A times P of B conditional A, which means that, well, suppose A happens first, or the decision maker first learns that A happens. This happens with probability P of A. And then, if A happened, if the decision maker knows this, then B happens with probability B, P of B conditional A. So WP means with probability P, B. And you can say something analogously for the second part of the formula. So this is P of B times P of A conditional of B. So this would be B happens first, with probability P of B, then A happens with probability P of A given B if B happened. Okay. Note that we have now two different ways of computing the probability of A and B. So we might be worried, well, we want to compute one thing, but we have two different ways. But because of the general multiplication rule, indeed we get that these probabilities are the same. Okay, so we never run into inconsistencies because of that. But it also allows us to compute the same probability in different ways. So for example, if you only know P of A and P of B conditional of A, you can compute P of A and B. But you could also compute it if you know the other two probabilities. So in practice, whenever you have an exercise and you know some of the probabilities, you have to figure out which formula you can use to compute the probability of A and B. Okay. And the last thing I would like to discuss today is Bayes' rule. Bayes' rule is a formula about conditional probabilities given the reverse conditional probability. Okay? So this is Bayes' rule. And again, this applies if P of A and P of B are positive. Strictly speaking, for this formula, we only need that P of B is positive. But if P of A was not, then this probability would not be relevant. So indeed, we need both of them. Okay? let me also give you the derivation of this formula. Indeed, this is pretty easy given the generalized multiplication rule. We call that by the general multiplication rule. There were two ways of writing down the probability of A and B, which was P of A times P of B conditional on A, or P of B times P of A conditional on B. Okay, and then we are almost there. We only have to divide by P of B on both sides. Then we get P of A times P of B conditional on A divided by P of B equal to P of A conditional on B, which is Bayes' rule. There is an alternative way to write down Bayes' rule, which you also see often in textbooks and which I also want to show you. This applies if you don't know P of B. Sometimes you don't know P of B, but actually you can compute it, and this is what I will show you now. So let me up. Okay. So this is the alternative formulation of Bayes' rule. Basically, this is the first part that we already saw in the last slide, and this is the new part. The only difference is that we replace this formula here in the denominator by PB. And let me also show you how we get there. Well, first of all, note that how can we rewrite the probability of PB? Well, suppose the event B happens. And how is that linked to event A? There are two ways. Either event B happens when also event A happens, or event B happens when event A does not happen. So in other words, the probability that event B happens is the probability that B happens and A happens, so A and B, plus the probability that B happens but A does not happen. That is the probability of the complement of A and B. Then, by the general multiplication rule, we can rewrite those probabilities. So P of A and B is equal to P of A times P of B conditional on A. And we can do the same applied to the complement of A and B. Okay. Again, use the generalized multiplication rule, replace A by complement of A, then you get, this is the probability of the complement of A times the probability of B conditional on the complement of A. Okay, so we know that PB is equal to this one. We can plug in this and this into this formula, and then we can plug this into the denominator in Bayes' rule. and we get the alternative formulation. Okay, this is all what I wanted to discuss today. First of all, are there any questions? If not, I will stay a bit around here if you want to ask me anything. I will upload any information about exam, FSRs, etc. on Blackboard. And yeah, I hope to see everyone next week again.
We are supposed to sign in.
Yes, this one?
Yeah.